All right, physics. Here we go. Round two of the Lorentz force. In the background there is a beautiful photograph of an aurora, something I would like to see at some point in my life. I've never seen one in real life. Um, Probably you guys haven't either, unless you've been somewhere near the poles of the planet. But at the very least, at the end of this lesson, you'll know how they come about. In the last lesson, we talked about the Philby force when an electric current of length L, a wire of length L, sitting in magnetic field B will experience a force F. Of course, the angle does matter. And remember, we also learned that the direction of that force is given by the right-hand rule. So remember, one that we're going to use, we're going to have your fingers represent the field, fingers for field, and then your thumb looks like a wire, represents the current, and then like Bruce Lee, the palm of your hand is the force, the direction of the force. Now the angle matters, and conveniently the angle between your thumb and your forefinger represents that angle. It's the angle between the current and the magnetic field. If you have to close your thumb down all the way down so that theta is 0, well, sine of 0 is 0. So when you have to close your thumb down, there is no force. Or if you like, if the wire is parallel to the magnetic field of your fingers, there's no force. And that's also true if the wire is parallel but opposite in direction to the magnetic field. There's no force in that case. Sine of 0, sine of 180 is 0. When your thumb is exactly 90 degrees, when the current and field are perpendicular, that's when you have the full force. Sine of 90 is 1, and just F equals ILB. Nice and simple. Oops. Now, I left you with this little problem. Here's a little negative charge, maybe electron or something, and it's cruising into this field that's coming out of the page. What's it going to do? Before I answer that, though, I'm going to do a little warm-up question similar to this one. I want to know what happens to a charged particle as it flies into an electric field. Now, this is something that you guys will be able to solve with what we've learned so far. So you already know, but I'll remind you, a charge that passes into an electric field experiences a force, of course. That charges get pushed by electric fields, and the size of the force is just QE. So here's the little warm-up problem. What would be the horizontal speed of a charge Q of mass m that is deflected a distance d in a uniform electric field E of length L? So I'm trying to find how fast this charged particle must have been going if it was deflected this much as it passed through this electric field. Now, looking at that field, the negative plate's up the top there, and this charged particle gets pushed down, so that must be a negative charge. I know that much. But the faster it's going, the less it would be deflected. A really, really slow one would be like, so I've got to find that speed. Now, I'm hoping you guys can recognize there is something very similar to what we've done before. This is actually a projectile question. That charged particle is going to be accelerated down. In a uniform electric field, the acceleration will be uniform. That's just like a projectile, except instead of gravity yanking it down, it's the electric field. So just like I do with projectiles, I'll get my horizontal equation on the board. So the thing I'm looking for, Vx, is really going to be equal to distance divided by time, L on t. I don't know what t is, so then I'm going to have to look to the vertical side of things. So vertically speaking, it moved down a distance d, and there's a familiar equation, ut plus 1/2 at squared. Conveniently, since I came in horizontally, there is no u, there's no initial vertical velocity, so I just have that. Now what would the acceleration be? For that, I'm going to need to borrow from Newton's law. Acceleration will be equal to the force divided by the mass, and the force of a charged particle in an electric field is QE. So acceleration will be Q on m, send that back in. Now I've got this, okay, d equals QE on 2m. But the thing I'm trying to solve is this, and there's a little bit of nostalgia for you. So I'll rearrange this guy for t, right, with the 2m up there, the QE down there, square root the whole thing, and then I'm going to shove that back up in there to get this. And that's what they were asking me to find. Cool, we just used electricity to solve a kind of projectile problem. That was fun. All right. Oh, is this like a legitimate thing that gets done? Yes, it is. So charged particles flying through electric fields is very common. This picture here is of what's called a cathode ray tube. It's actually how we discovered the electron. You got a really, really positively charged anode and a really, really negatively charged cathode, and that's so negative that electrons get pushed off it and they get attracted to this positive anode, and they pick up speed, but there's a little hole there, so they get accelerated, accelerated, accelerated. Some of them get accelerated towards the hole. As they pass through, the field's not that strong on the other side, and so they have enough oomph to keep going, and they fly across here. We put a chemical on here. Little electrons hit the screen and make a blip. You may have seen them in something like this, like a heart rate monitor. It's just a beam of electrons flying at a screen, and we get the blip by putting another electric field vertically to show what's going on. Gosh damn, it's so professional, isn't it? With this drilling in the background, it's wonderful. This is an electron gun. We're going to meet one of these later on. The same sort of thing though. You've got like a really negative anode here, positive thingamajiggy here. Electrons get ripped off, and then we have these like little donuts, a negative sort of donut here that will condense this electron beam, positive one, which will expand it, so we can focus this electron beam, get it parallel, and we can shoot electrons at things we want, which we do want to do. We'll do that later with electron microscopes. Anyway, let's get back to the main thing that this lecture is about, which was this guy, this charged particle flying into a magnetic field. You probably guess it's going to get deflected, but the question is how. And maybe you're busting out your right hand right now trying to figure out what that thing's going to do. But we use the right hand rule for conventional current. Conventional current is really positive current, and so we can't use the right hand rule to figure out what way that thing is going to get deflected. We're going to need to use our left hand because it's a negative charge. But so it's the same rule. Fingers are still field, thumb is still current, but because that's a negative charge, I have to use the opposite hand. The force will be in the opposite direction for a negative and positive charge. And so how should you be orienting your hand? Well, your thumb now represents velocity. Fingers still represent field. And so you should have your hand like that. And that little guy is going to be deflected when he flies into that field upwards. So charges get deflected in magnetic fields, and we can figure out a formula for individual charges from the one, it's really, really easy to do this little proof here. If you remember that current is just charge per time, coulombs per second, the coulombs per second passing through a wire. So I switch that out, and then I notice I have L on T, distance divided by time, distance divided by time. That is really just velocity. And so I get F equals QVB sine theta. That is the Lorentz force for a charged particle moving at speed v through a magnetic field. Of course, the angle still matters, but it's not the angle between current and magnetic field. It's now the angle between the velocity and the magnetic field. So same as before, pretty much. And yeah, the sign of the charge will determine the direction of the force. So you have to use your left hand or negative. So positive and negatives get deflected opposite directions. Here's a positive and negative charge flying to the right through a magnetic field that is into the page. I don't like that they have circles around that. Anyway, I digress. What I want you to notice, check that they've obeyed the right-hand rule. So yep, this one here, chuck my thumb to the right, fingers into the page. Yep, my palm is upwards. For the negative charge, chuck my thumb to the right, fingers into the page. Yep, my palm is pointing down. Notice something though. Notice that the force in both cases is perpendicular to the velocity. So they're flying that way and the force is perpendicular. What does that remind you of? That is a centripetal force. When the force is at right angles to the velocity, you have a centripetal action going on. So charged particles moving in a magnetic field get pushed around in a circle. You might remember this. This is a beam of electrons flying up. There's that anode attracting them. So I've got a beam of electrons. If you switch on a magnet sideways, you get this beautiful circular path for the electrons. You see a circle, you know that net force equals mv squared on r, and now we know the force actually ripping that thing around in a circle is QVB. So this little experiment allows you to solve for perhaps the mass of an electron, which is a handy experiment because you just have to measure how fast was it going, which we can calculate from the electric fields, and the size of that radius. Real easy stuff. I was going to make you guess the direction of the magnetic field, but I already showed you. It's like, okay, so that must be into the page. You can check if you're an electron flying upwards here. Right? Which way do you get deflected, or which way must the magnetic field go? Well, I've got to use my left hand. My thumb is up because that's where that electron's going. I know it gets pushed to the right towards the center of the circle, so my fingers must be pointing into the page to get that. So that something interesting pops up here. That means charged particles spiral around magnetic field lines. That's what happened here. They're spiraling around the field lines. If the charged particle has any sideways velocity, parallel velocity to the magnetic field, it doesn't go around in a circle, it goes around in like a springy spiral. Only the parallel component of velocity parallel to the magnetic field actually gets pushed. Any component of the velocity parallel to the field gets no force. And so if you like, its horizontal velocity is sort of constant through here, and vertical velocity is spinning around in circular motion. This is pretty darn important for our survival because charged particles are cruising towards Earth all the time. When they hit the Earth's magnetic field, they spiral around it. They experience that QVB force, and they spiral around, and they spiral around the field lines, which are bendy in Earth, and they come out of the poles. And so charged particles are directed towards the poles of our planet, which is really cool because it leads to this. When those charged particles hit the Earth's atmosphere, they glow green, like that cathode ray oscilloscope. This picture here, I'm pretty sure is fake, because you'd have to be a really long way away from Earth to take that. I'm pretty sure that's just CGI. This one is not. This is not. This is real. That is a photo from the International Space Station, I think. That's just beautiful. That's super, super cool. There's another one. Oh, pretty. This is greatly exaggerated. Obviously, Earth is way further away and way smaller, but that magnetic field, as well as giving us auroras, also makes our planet habitable for life as we know it. The solar wind that blasts planet Earth is directed basically over and around planet Earth, and occasionally some will sneak down to the poles to make those auroras, but our magnetic field blocks this charged particle wind coming from the sun. And if it didn't, I hope you weren't wearing headphones. Anyway, I'm moving on before that guy keeps gosh darn drilling. Some particles go over the top, some get spiraled down. Yay. I put a link in the thingamajiggy to show the difference between Mars and Earth. Earth gets protected, Mars gets wrecked because they don't have a magnetosphere.
Our sun is...
I also put a link to NASA's satellites that are investigating our magnetic field, these 4 synchronous satellites. Pretty cool. So yeah, that's it. We saw charged particles in electric fields behave like parabolas, like projectiles, and charged particles in magnetic fields move in circles. 2 things you guys already understand. No questions today. If you have time, have a read of the chapter. Otherwise, happy quarantine, kids. See ya.